okay, for those who have close contact with the cases, right? You are allowed to attend online, like I said, but still go through the official channel, let the faculty know that you are under this close contact list, okay, so that you are okay not to come to the physical class. Okay, so let us continue with our DC to AC converter. Okay, we have done through the push-pull, all right, DC to AC converter. And we have also done through the half-bridge topologies, all right. We also gone through the full bridge, all right. And we have gone through the simple equations to calculate the VRMS and a total harmonic distortion. Okay, we also gone through the simulating implementation, okay, of this full bridge, half bridge, and so forth, so that you're aware that, okay, how you can construct a DC to AC converter. Okay, today we will move on to this SPWM. Like I said, the problem with the normal, okay, DC or conventional, traditional DC to AC is that they produce square wave. The problem with square wave is that it has a very high total harmonic distortion, which is near to 50%, which is very, very high. For TMB or grid connected, your THD must be less than 5%. So 5% to 50% is 10 times. Okay, so you can use it for low power application, but you cannot use it for grid connected or any equipment that require a sine wave output. So to solve this problem, we need to switch. Okay, now you can see that we are performing switching to this 4 transistor, right? Okay, so we need to switch them in a way that they can produce a sine wave output. So to do that, it is going through a modulation technique. Okay, so modulation is a very old technique, started in the era of radio communication. Now, in the old days, our very first radio transmission was the AM radio, okay, amplitude modulation, where we still use it today, okay. So the other types of radio transmission is FM, okay, FM frequency modulation, okay. So again, like I said, modulation, right, changes the frequencies, okay, to use a higher frequency to carry as a carrier to carry a lower frequency component. So for the same, okay, we use PWM, pulse wave modulation, okay, as a carrier frequency to modulate the sine wave, okay. So to do that, of course, the easiest way is that the good news is that MATLAB already have this function block for us. Okay, so this function blocks is the PWM generator 2 level. So what we are going to modulate, we want to modulate the sine wave. That means sine wave is the signal we want to modulate. So when it pass through this SPWM generator, it will generate, okay, it will generate this, what we call modulated pulse. And it comes up with 4 channels. Okay, why 4 channel? Because we are using this full bridge. Full bridge require 4 transistors, right? So they help us to switch. So here you will see that the setting. Now for the modulator, okay, we call it PWM generator, 2 level. And then this is the modulating signal. All right, so we want to remember the modulating signal must be higher, okay, than the signal we want to carry. All right, so at least by Nyquist theorem, at least it's double of the frequency, okay, of the original signal you want to carry. So usually we will make it a few 10 or 100 times higher lah, so that, okay, it can, what we call, the higher the switching frequency, right, the carrier, the higher the clarity or resolution. Now, for example, for FM radio start from 88 megahertz, right, to 108. But our voice, our music frequency is only up to 22 kilohertz. Our voice is roughly around 1 kilohertz. But you see the frequency used to carry it is megahertz. So many times, right? That's why FM radio have the most clear stereo quality. But AM radio is in kilohertz, right? It's in kilohertz. It's very much lower, but still higher than our voice and the music we hear. So it's able to transmit, but the quality is not that clear. Okay, so that is the reason. All right. Now, of course, that one is for radio transmission under communication. Even for that one is analog modulation. Now, our handphone nowadays is using this shift keying, minimum MSK, minimum shift keying. It's a digital modulation. Okay, so for this, our GSM, because we are still based on the GSM standards, okay, it's around 1.6 megahertz. Okay, so again, you know, it still modulate our digital voice, okay, transmit and demodulate to get back the signal. So the same concept and theory apply for inverters. Now, the good thing is that frequency is fixed, okay, 50 hertz or 60. All right, so that our switching frequency, okay, we can put as long as higher than 50 will do. Then, of course, we know that the higher you go, the better resolution you get. But there is a problem, right? The higher you go, the higher switching loss you get also, right? So there must be a balance point. Typically, those industrial, what we call this inverter, they run between 5 kilohertz to 20 kilohertz. That's already the best so far that can use for the grid. Okay, so later we will see. So this is now because of lecture, I make 500. Otherwise, you all cannot see. Okay, it's so high frequency, so I intentionally make it so low. And then, of course, this will be your sine wave, okay, amplitude 1, and then the frequency 2 by 50 hertz. Okay, so that is your signal I want to modulate. You got sine wave in, but you got pulse wave modulation output. So this will be the resultant output. Now, I have a sine wave. As the sine wave, okay, move higher, you can see that my pulse wave become wider, right? Wider, and then when you go back low, and when you go to negative, it becomes smaller. You see, this is the pulse wave. It becomes smaller. It can become smaller and until the smallest point. So this is how it works. And then this process repeat. Because the good thing is that, okay, our grid frequency is fixed. Now, for radio communication, for satellite, okay, or our handphone, our voice frequency changes. Okay, ladies' voice was slightly higher. Okay, their higher pitch, so their frequency will be around 2 kilohertz. For male guys, okay, it's roughly around 1 kilohertz. So when we talk, right, our frequency change. Okay, so it becomes actually much more difficult, more challenging, but not our scope of this inverter, unless you are focusing on the communication side. Okay, or then you need to deal with all these problems, how to make it transmit for efficient. Okay, now how this modulation works. Now, there is a way to calculate them. Let's see. The first thing we want to know is modulation index M. This is very important because you will have this, unless I change this one, you will need to put in the modulation index, okay? Now, the modulation index is equal to the AC peak divided by your DC source. Okay? Now, let's say we want to modulate sine wave 230 RMS. So our peak is 235. Then our DC source, which is the source of the inverter here, this DC source. Remember, the DC source must be greater or equal to your AC peak, or else you will never be modulate them properly. Rule number one, okay? So in this case, typical, they will modulate them, the DC source is 400 watt. So 335 divided by 400, we get a modulation index of 0.815. Very important equations. Okay, now the next thing is that we need to know the time for our frequency. So very simple, right? 1 over F. So for 50 Hertz, our time is 20 milliseconds. That's mean this whole cycle here, 20 milliseconds. You see here, 0.02, 20 milliseconds. Then our SPWM, which is our carrier frequency or switching frequency. There are many terms, okay? For those who are specializing in modulation or those who are in communication background, you will say what is the modulating frequency or the carrier frequency. If you talk to power people, you have to tell them what is your switching frequency. It's the same thing. It's just the language went into different area. Okay, they speak differently. Okay, so make sure when you talk to a person, right, if you know his background is comm, you say, oh, what is the carrier frequency? If that guy is electrical background, then you tell them what is the switching frequency. All right. Now, switching frequency is 500 Hertz, right? So 1 over F, you get 2 milliseconds. Now, these two very important, because these two will tell you the number of sample you get. That means, you see this one sine wave, right? It will produce 10 sample because it is 20 milliseconds divided by 2 milliseconds, you get 10. That means this whole sine wave, right? You actually chop them into 10 pieces. You can see 1, 2, 3, 4. Okay, if I write here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You chop them into 10 pieces. Now, the higher frequency you do, if I increase this one more zero, you chop them into 100 pieces. Okay? That means more higher resolution. It's just like megapixel. You imagine this is a picture. You take this picture with only 10 pixels. You cannot even see the face, right? But you increase it to 100 pixels, you maybe roughly can see the shape. Then you increase again to 1000 pixels, most likely you already can see the face. Okay, so that's the idea. That's the idea. Now, you know that in this case, You split that, you can chop them. Okay, this is how we calculate them. So each sample cycle is 2 milliseconds, right? So you can see that from 0 to 0.002. So this is 2 milliseconds. Okay, so this section, the first piece. Now, how do we know the duty cycle of this piece and the magnitude of this analog side? First of all, the first piece is between 0 to 2 milliseconds. So we take the midpoint, the central point. So the central point is here, right? Is 1 millisecond, in other words. So it's 1 millisecond, that is the central point. And then you calculate the duty cycle here. The duty cycle D bracket T. Okay, the T refer to the time, the first slide here, T1. Okay, so this is your T1. And then 0.5 multiplied by 1 plus M sine 2 pi FT. Okay, so if you get all this correct, you will get this number. So it tells you that this modulation is 0.6255, which is 62.55%. All right. And then for the V, okay, this one is the PWM value. And this one refers to if 0.622 equivalent to how many volt here? Okay, equivalent to how many volt where the peak is 325. Is AC peak multiplied by sine 2 pi FT. Okay, so this is the time. All right, and then if everything is correct, you will get this number. Okay, so up to this point, any questions? This is very important. Okay, so it could be one of your final year questions. And this question, if it came out, I mean, you can look at the past year. You need to calculate all 10. 10 pieces here, every step, pop, 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 pop. Okay, because anything less than 10, very hard to calculate already. Too low resolution. So this is the lowest I can set for the final exam. Okay, like I said, very important. You have to make this out correctly in order to get these two numbers confirm correct. But I don't know how you ought to fit this value. So please do it and make sure you get this number. Okay, now I work only up to 3 steps for you to verify. Okay, first step is like that, right? Second step, I move to the second piece. So this is the second piece here. So this one same, this one same, this one also same, okay? But this one different. This one T is 3 milliseconds, right? Previously, this one is 1 millisecond. Because the second piece is 2 to 4, so the midpoint is 3. Okay, so the midpoint is 3 milliseconds. And then again, the equation is still the same. Okay, and of course you can see now, 1 is the same, modulation index is the same, 2 pi f, t different, right? That's mean 2 pi f t okay, which is the omega t, okay, are different. So you can see that at here is going to 0.82, obviously, and because the magnitude is higher, right? And same thing, when you calculate this, it represents 262.9 volts. Okay. Now I move to the third step. Okay. Third step, come back here. First step, same. Second step, same. Third step, same. The fourth different. So when you do your final question, right, you no need to repeat the first three steps because it's the same, right? The first three steps. You only need to repeat the third sample. T is equals to 5 milliseconds. And you do that, you can see that, right? The duty cycle is 90% already because it's already reached the peak, almost 100%, right? And then you will see the V is already 325. Now, Y is already 325, but your D is not 100% because your modulation index is not equal to 1. It's equal to 0.81. That's why, you multiply it, you get this number. All right. So you continue. Okay, I work until 1, 2, and 3. Okay, 4 I didn't work out because it's a repeating process, like I said. Okay, the only difference is the T. Okay, so please work out the rest by yourself. Okay, so that you will know how to calculate this. Okay, how this modulation, okay, duty cycle and its equivalent voltage, okay, are calculated. All right. Okay, so up to this point, any questions? Because it's not practical to calculate the 100 pieces, right? But at least you know these are the fundamental. Okay. Wow. No question? Online? Student?
Yes, sir. Hello.
Yes.
I'm slightly confused on the AC peak part. So can you explain again?
Sorry, I can't hear. You can speak louder. My audio is already 100%. Wait, speaker, Realtek, let me change. Wait. Okay, can you speak again? Hello? Hello, I cannot hear you. Anyone try to speak here? I can't hear everyone here.
Hello, sir. Can you hear me?
Can. Oh, I thought my speaker got problem. Okay.
He say he confused about the SC pick there.
Okay. This one, right? Okay. The difference is that now you see, this duty cycle 0.9 represent they see this is digital Okay. In other words, we call digital. This is a digital value, right? In duty cycle 0.9, and this 0.9 represent, okay, the AC or the analog side of 325 volt. There's a difference between this. You can see here, this is the peak, right? Now you want to modulate, the peak is 325, right? So you can change this one, okay, depend on which country you are. So this is how we get our modulation index. And this digital output, this is what your 4 transistor is seeing. Okay, when you demodulate, right, you will see back the sine wave. So there's a difference between these two. So this is analog. Okay. Can you understand? Imagine a modulator. Okay, you got sine wave in, right? and you got the PWM output like that lah, okay? Okay, this is modulation. Then of course, we have a demodulator, right? A sine wave in. Then you can reproduce the sine wave out. So now we are doing this part. Sine wave, digital output. And this digital output to switch, okay, the half bridge. All right. Anyone answer your questions?
Yeah, I think okay, sir.
Okay, okay, later slowly you will see. Okay. Okay, now like I say, the importance of this one, make sure you all know at least like, if you are lazy, you just at least do these 3 steps lah. Okay, the rest you just need to do it yourself. Okay, now if everything is correct, right? You can see this is the modulator, so you got the 4 output. So you will see something like that. You can see this is 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and you can see that the second one is the opposite. Okay, the inverted version. Okay, the inverted version. All right, the inverted versions. So this will be for your first transistor Q1, and this is your second transistor Q2. And then you will see the third one is the opposite of the first one in the sense that you can see it starts from 10, 9, 8, 7, which is mean that the Q1 and Q2 it modulate a sine wave in this way. And this Q3, Q4, these are all transistors. Q1 and Q2 will never turn on at the same time. Okay, it modulate in this form. You can see is out of phase. That's why you see the lowest negative come first and then go back to positive. And then this one again inverted to each other. So with this 4, Q1, Q2, Q3, Q4, it is going to connect to this. Okay, so usually this is on the Q1, Q2, Q3, and Q4. Okay, so you connect them, so they will switch. All right. Okay. Now, like I said, the good thing is that Simulink already provide us these magical blocks for us to do modulation. But like I said, we still need to know how this thing works inside. So I just put in an effort, okay, to show you how this thing works. Now you can construct this by yourself, okay, using a sine wave here. Now you can see this is a sine wave. And it passed through a what we call relational, greater and equals, to the triangular. This is the modulating signal, triangular wave. And here you will see there's a -1, right? It will convert the sine wave to out of phase. Okay, 180 degrees. Doing the same thing here. And the output, okay, is based on this function. Okay, the SPWM output is equals to 1, where your sine is greater than the triangular wave. And it's 0 when the sine is lesser or equals to the triangular wave. All right, so this is how you construct them. Okay, and then when you see the output, okay, these are the blocks that you're going to what we call creating, okay, the triangular wave here. These are the frequency lah, like I say lah, your 500 hertz or so for the switching frequency. So after that, now you can see the blue color is the triangular wave, okay, and this is a sine wave. Now it actually compare, right? Now you see the first portion here. The sine wave is greater than the triangular wave, right? At this point. So sine wave is greater than the triangular wave, means 1. So it will switch to 1 here. You see at this point? If you draw a line, you will see that it is like that at this point. You see it's high. When this, okay, yellow color is lower than the blue color, you see it becomes low. You can see if you draw a line, it's like that. And this process repeat, you see, it repeats itself. Okay, it repeats itself, and this is how you get to modulate your sine wave. Okay, to produce the SPWM. All right, this is how you produce a SPWM. All right. Okay. You guys want to try this or not? I don't know. Or you may think it's a waste of time because it is already, let's see. Okay, I'm not sure got enough time. Wait, let's see. Okay, I think we skip this one. You can try it at home lah, because this is just for extra knowledge. You know, you can create yourself. I think we will spend some time to do the modulated version because 5:45. I got another 45 minutes to go. Okay, so this one extra knowledge because MATLAB already have. Okay, this is just to give you insight what is inside there. Okay, now I think the best thing is that let's do this one. Now this one, you know, you already created the full bridge, right, last time? Now you use this SPWM output, okay, to connect them. Now if you connect that correctly, remember the switching frequency. If you use 500 hertz for your switching frequency, you will see that the output of this, what we call this inverter, you will see something like that. Okay, so each of them, you know, will have 10 pieces, 10 pieces. Now, if you change your switching frequency to 5 kilohertz, you will see something like that. Of course, this one I increased to 0.1 second. You can still make it at 0.02. Then you will see that because this is a higher resolution. Positive, negative, positive, negative, positive, negative. Okay, so please do that. Okay, now and see you can produce the same result or not. Because this is a very important part. Okay, let me just. Okay, All right. So you need to choose the PWM generator 2 level. So I think I need to just make it visible. Okay, the 2 level, and of course here, okay, now it's 5,000 now. Maybe we start with 500 first. Okay, we start with 550 Hertz. We already know that they'll produce SPWM, right? So we will run this. Okay, let's say I run it for 1 cycle, 0.02. Okay. All right, you should be able to see this, Okay, output. Now, if I change this to 5,000, that means I increase another 10 times, higher resolution. I run again. And you can see that, okay, you can see that it is already chopping it into 100 pieces instead of 10. So it's higher resolution. Of course, you increase the time, you see the repeating cycle. Okay, so please do that. All right, and show me in your chat box. Try with the 500 Hertz first. For those already done, this bridge should be very simple. You just need to change this part. So I do have get the negative value. Interesting. Something is wrong in your calculation. So this, after you know how to do this, you will know the immediate application, okay, of this type of modulation already. It is widely used in many industrial applications. So later I will show you what is the direct application of this. Wow, some of you guys signed on 3rd of February. Hey, come on, guys. Don't do that, leh. You know, when you all sign, right, please look at the date. You don't sign on those dates, you are not supposed to come. I know that you want to sign for today, maybe, please lah. I will pass them around again. Cancel those if you sign wrongly. You don't get yourself into trouble. I tell you, you had to explain until, you know, how you magically come on that day where there's no class. And some more physical, you know. So please, okay, I will pass around again, Osama. Please rectify it right now. Because after today, it's difficult already. Don't sign on the day you are not supposed to hear. Oh, good. We already got one student done already. Very good. Okay, you can try the 5 kilohertz. Okay. Okay, Tan Kai Hong, very good. Like I said, if you follow my exercise, you should be able to create, like, it's less than 5 minutes. But of course, if you start again from the hard bridge, it will take longer lah. Okay, how about the rest? I only see one student doing it. Two students, okay. Okay, very good. Of course, as you increase the frequencies, you won't be able to see, because let's say you increase the frequency with another 0, there will be 1000 slides per half cycle, unless you can see, unless you zoom it in. Okay, you zoom it in detailedly lah. But like I said, so far I didn't really see any inverter using 50 kilohertz. Most of them is within 5 to 20 kilohertz. Okay, good. Alauzi Muhammad, right? Okay, very good. Okay, we got more coming in. Okay, Fu Tun Hao. Okay, good. Okay, on Wk6.1. Okay, Oksama. Okay, very good. So the one of the thing you have to take note is that when it comes to hardware, right, these 4 connection is very, very important. Okay, not to connect them wrongly, because really the 4 connection, right, if one of them wrong means 2 wrong, right, because there are 4. So you will cause short circuit. Imagine if you really have a 400 volt there, short circuit, right, what will happen to the transistor? So we really have to be careful when you are dealing with hardware. But I think it's okay for this semester. We're not going to do any hardware, okay, which is good news for some of you and also bad news for some of you who really want to learn hardware lah. This one, like I said lah, you have to check, okay, which part you get wrong.
Doing it the other way, but it's not connecting.
You don't do it in other way. You want, you follow this way. You don't go and play around with other way and ask me why it's not working.
The other one, the SPWM. This block. This one.
I can't tell you. If you want to do it in a creative way,
Not creative,
I mean,
doing halfway already, so. Okay.
don't do that to me lah, okay? Or you want to challenge me? I admit defeat. I admit defeat.
I'm not challenging you lah.
Yeah lah, I mean.
Just trying the other one you say.
Then I can't tell you why lah. Okay, I think I need to move on already. It's already 6 o'clock. Okay, for those who work it out, good job. Okay, so now maybe we will move on. Okay. Okay, like for those who already work this out, you should be able to see the difference between a lower switching frequency and the higher switching frequencies, all right? So these are all in MATLAB Simulink. But if you consider to do this hardware, right, so you will need to learn 2 things. First is that you must learn how to program the hardware directly using this Simulink. So Simulink allows you to directly program to Arduino and some other microcontroller without you to writing a single line of code. So that's the beauty of this Simulink, okay? And secondly, you can choose to write code as well, all right? Here I just briefly go through, okay? Because I say we are not going to do any hardware, but already prepared the note anyway. There are 2 Arduino and Arduino Mega is a very commonly used. The good thing is that they are also designed to produce PWM output, okay? They are also designed to produce this PWM output. It has 6 PWM output. Why 6? Because it's designed for 3-phase as well. 6 transistor, okay? Our full bridge is 4, so it's more than enough, actually. So yeah, if you want to do that, okay, you need to, to download this Simulink support package from MATLAB. It's free, okay? And after that, of course, these are the pin selection. You need to know the pin detail and have to understand how the PWM works. Okay, the limitation of if you are using Arduino, the selection of frequency is limited. For example, you cannot say, I want to choose 10K, 20K, or 5K. Cannot. It is fixed into like 976 or 7.8K or 62K. Okay, so this is a limitation of using Arduino. But for us, it's good enough lah. We know that 7K is greater than 5K, right? You get a quite good resolution. So there are a few frequencies we can choose, okay, for the modulation purposes. Okay, so these are the internal register which I'm going to skip. And then remember MATLAB, we can build our own blocks, right? So here we are going to build a blocks that you can connect to Arduino, okay? But the detail you can do it when you are free, because this one requires some simple coding here, okay? You could require to do some simple coding. And you can actually create, okay, blocks, all right? Something like that, Arduino PWM generator, okay? So that you can connect the output. You can see that in your Simulink, right? You can set, you want to program to Arduino. You can have hardware implementation. And then if everything is working correctly, it works in the concept something like that, okay? You have a model, okay? You have a model like this one, okay? Create in MATLAB. And then you can download into Arduino through the USB cable, okay? Directly connect to the USB cable. And then you can measure the PWM pin using oscilloscope. And the oscilloscope should be able to show you what you see just now as you are doing in your software. So I have actually proven this, okay, using the scope. This is the actual scope that I capture and save. You can see the date is 2021. I get it done during the December. So you can see that, okay, so these are the, okay, the frequency is 990 Hertz. All right, slightly higher than 500, but you still can see the modulation, right? The pieces that it chopped. And of course, as I increase to 1.9 kilohertz, you can see it becomes denser, 3.9 kilohertz. Okay, 7.81 kilohertz, 31 kilohertz. You can see it's very dense already. All right. So I think I didn't go up to, because the maximum you can go is 62K. So if this one is correct, what you need to do is that you just need to connect those pins to this 4. Of course, remember there is a driver circuit. You need to put in the MOSFET driver, so that you can create your hardware, okay, bridge. And then, of course, these are the driver information. You need to get this chip, okay, the driver chip. All right. So that is about the hardware part, okay. Maybe I got time, because I already created the block. Why I still never put up on the MATLAB. Maybe next time I put out, you all can download and use it. Okay, now like I said, once you get the what we call this SPWM done, right? It's already widely used in the industry already, just like that. Okay, one of the application is VFD, stand for AC Motor Variable Frequency Drive. Okay, now VFD are widely used in the US. And VSD widely used in Europe. They are both the same thing. Okay, now if you want to buy this from ABB or Schneider, Europe country, right? So you say, I want to have VSD. So VSD stands for variable speed drive. VFD stands for variable frequency drive. So this device, physically, it looks something like that. Okay, this is a real device. In fact, I have one in my office. And then inside, okay, it has a AC to DC converter, which is a rectifier. And then it goes through a DC to AC, which is the one we are doing now. Full bridge inverter. Then it connects to a motor. Okay, it connects to the motor so that you can control the motor speed by changing its frequencies. So they say variable frequency drive. Now, our frequency is 50 Hertz. Right? If we want to change to RPM, we multiply by 60. We will get 3,000 RPM. So if we want to change it faster, we increase the frequency. We want to change slower, we change the frequency. Remember, the purpose of this, okay, is to change the speed. Because we cannot ask TMB, can you change the frequency to 30 to slow down a motor? Cannot, right? The frequency always 50. It got two purposes. One is to change the frequency, okay? Now, secondly is to make sure that it is efficient in terms of controlling, okay, the motor. Now, there are a few YouTube links here. Okay, maybe I will see, okay, this card. Okay, I think I need to include the audio. Hopefully the link is still there. No, sometimes the link is no more there, then it's a bit susah lah. Okay, include audio. Okay, let's see. Okay, I need to copy. Come on. This is one of the devices that many of the industry is using right now for energy efficient. So this is a typical, what we call this single-phase to three-phase motor, induction motor. Okay, we split the connection part. It's still how it control the speed. So you can see that it's running at 49.5 gig frequencies. Now you can see it's getting slower as the frequency reduces. So we change the frequency, turn off. Now you can see turn on and rotate. Now the good thing of using this is that it will not cause an inrush current and sudden spike. When you turn on a motor, it straight away jump. You slowly increase it. So it reduces what we call the inrush current. Suddenly, imagine you're turning 10 motor at the same time, what will happen to the system? We will trip, okay, because of the inrush current. So the good thing is that if you are using a VFD, you have this advantage. Okay, let's see the second one. Okay, let's see this one. Okay, I think this one is more on operation, connection. I think we'll skip this one. Oh. You can see that it rotates, based on the frequencies. Okay. 50 Hertz is 3000 RPM. And you can see the voltage, the current. I think nothing much on this video. We just see the third one. You all can watch it at home lah. If you want to see the detail, I'll just do a few. You can operate like 30 Hertz. Okay.
As a result, industry law. Here we have a fan-based
machine. This one is a very important application. Okay, this ABB demo is the one that I like most. It compared two different drives. Okay, one without VSD and one with the VSD. How you can make efficient? You see, this is a motor, and there is a fan. This motor produces a wind blow. It put a balloon here. Okay. If you want to control the balloon at certain height, right? In the old days, not old days, even actually including many of the building I see before for some of my consultation work, we are still using this system. Even big mall, shopping mall, the aircon, right, blowing, is actually using this what we call valve, mechanical valve. That means the motor is 100% on, but it's so cold they use the valve to control it. So this is what happened.
Using a balloon to demonstrate the potential energy savings of a variable speed drive versus a conventional damper control system. Here, the ABB drive controls the speed of an electric motor, which in turn drives a fan, which pushes air through this duct. Now, within the duct is a mechanical damper used to restrict airflow. Dampers are commonly used to control airflow in industrial applications. Here, the PLC collects all this information to be shown on the operator panel.
There are two
now, let's start the system up.
To show the power consumption. So when it turns on, so you can see that the balloons go up and hold up there.
First, we run the motor at a nominal speed with the damper fully open.
So this is maximum
Here,
power.
We're measuring input power.
So you can see now the motor, right, without any control, you turn on, it gives you max power. So the motor will take, let's say, 107 watt.
As you can see and hear, there is far more airflow than is actually needed to keep the balloon at the reference level.
So
this can be caused by possible oversizing and sizing for worst case conditions. Now I'm going to reduce the airflow to the reference level by adjusting the damper.
So now they use this damper to block the wind, so the balloon will go down to this level.
As you can see, the current power consumption is about 100 watts.
But you can see still the power no change, right? So you see in the industry, all these things we call AHU, air handling unit. okay, including our block A, I can see they are still not using variable. They're using damper. The moment I turn on the aircon, even we put the fan very low, we are still taking the maximum power. So this is what happened right now. Okay, because in the old days, that's the design lah. Okay, that's the design. And then people feel that variable speed drive is expensive. I want to buy a lot, they don't want to spend this money. Okay, then you'll see what happened.
Next, we stop the damper control,
Now,
open the damper fully,
open again, full again.
and turn on the ABB drive controlling the motor speed.
Variable speed drive. Now you just control the power to the motor. You get the
By maintaining the same balloon height, we confirm.
You see, you get the same airflow, but you only use 40 watts. Just now is 100 watts. Huh? How many percent you save? 60%. Okay, it's a lot. Huh? Electricity for shopping mall, we are talking about few 100K per month. UCSI itself, just nothing as far as I know, 120K a month. If they're using variable speed drive, you know, it's going to less than that lah. Okay, so this
the airflow is the same. Firstly, there's a lot less noise, but more importantly, in this case,
and also important is that you use variable speed drive, you control the speed, lower power, lower noise. Remember, the aircon is very noisy, right? At night, you know, wow, maximum. If you use damper, okay. So hotel,
there's a power saving of
they're having this problem, okay?
Around 60%.
60%.
As you can see, the variable speed.
Of course, a lot of clients, they just think, I want to buy one drive. It's actually not very expensive, just a few hundred ringgit. Just really just a few, but to them, if they have 100 in the shopping mall, they think it's expensive lah. But consultant always say, you are the customer, right? You are right. I just tell you, if you say expensive, I give you all one. Imagine if you spend that 100 in a year, the money is saved for electricity is actually much more lower than you used to pay for the drive. So as a consultant, this is something you all should know lah. Okay, but yeah, we are not doing consulting costs. Okay, but this is some, I don't know lah. This is the Malaysia culture lah. They just say, no, we don't drive. Expensive. Okay, lor. Then they pay TMB, they say good. Or later they claim why TMB charge me so expensive. You know? So this is
drive achieves the same process throughput with significant energy
application of what I showed you just now. Okay, you may tell me, say, sir, you only show us the 4 transistor with just switch like that. Where God? Okay, no worry. I created, okay, in the note here, I show you how this thing works. It consists of 2 stages, AC to DC converter and DC to AC converter, okay? And then it is considered AC drive, all right? It is lightweight, okay? It's actually inexpensive, low maintenance for AC motor, all right? You can use for induction motor, synchronized motor, and of course, there are various of control you can do. Okay, as for our power E, we are focused on frequency control for today. Okay, you can control the torque for those motor that handling conveyor. But for fan, like I say, mostly in the market, the problem is the fan actually. So VFD is actually good enough to solve this. They also have direct torque control. They also have vector control. Okay, so as for this one, okay, direct online means this is not the internet online. Direct online, like this one, they connect the motor without any drive, 100% power, okay? So this can be done, okay, I created this VFD for single phase induction motor, exactly the one ABB they show you. This is how the thing works. You build it yourself, it's very much more cheaper than the one you can get, okay? Now, okay, this one, while I'm explaining, please download it here because I just uploaded it last night. Yes. I also do last minute work, like you guys. Okay, remember you go to the MATLAB file exchange, right? Okay, please download while I'm explaining later. I think not many variable speed drive is in this. If you type VFD or the full word of variable speed drive, you only see 1, 2, 3, 4, only 4. I think I'm the one that really show how this thing work. Okay, you find the one Rodney Tan here, uploaded 6th of February. So please don't waste my effort last night. Initially, I was thinking to ask you guys to do in the class. But after looking at you guys doing this in the class, I mean, the response is not so good lah. Even just now, there's less than 10 students doing it out of 100 students. 10%. So I'm a bit disappointed lah. But never mind, because you all choose not to learn ma. So I gave you the thing lah. So later don't blame me Say, sir, why you never teach me this and that Okay, please download this. Okay, support a bit. And then, okay, let me just explain. Now, how this VFD works. Now, this VFD works very simple. You can see that this is the AC. Okay, I think I will use this one to explain better. Remember, I say power electronic, usually they consist of more than one stage to make up a complete system. Okay, now you see there is a full bridge rectifier at the first stage. Okay, where we connect to our AC 230 watt. Okay, and then okay, the 325, and then we will have a filter capacitor. So that's mean from here we will have around 332 watt. And the 4 bridge is here, very simple. And the modulation you all have done is here. Okay, so the modulation index I also put around 0.8 lah. Okay, I modulate at 5 kilohertz. Okay, I modulate at 5 kilohertz, 50 hertz frequency. Output here, there is already a induction machine, single phase induction motor. I don't do any change. Quarter horsepower induction motor you can find in the market. Okay, quarter horsepower looks something like that. It's 0.25 horsepower induction motor. Okay, you can easily get this in many of the shops out there because it's one of the very common. Okay, these are the induction motor. How it looks like? Okay, this is how it looks like. It's that big I also have one in my office. Okay, and then now, of course, these are the mechanical part. We have sim electrical, we have sim thermal, right? We also have sim mechanic. Now, these are the few parts. Okay, I can decide the torque. The torque I put as default as 1. Okay, this one I just put as 1. And then the output of the motor, all right, this is the RPM. Now, I measure the voltage, I measure the current, all right? I run this for 1 second. I run this VFD for 1 second. You will notice that the RPM is almost like 3000 something, right? We fit the frequency. Okay, you will not get exactly 3000 now. It's a rotating device anyway. Okay, so you get roughly like 3045 plus minus. It fluctuates because this is a induction machine or mechanical part. And then the thing is that you look at the waveform. You see, the beauty is we get sine wave current output. You see? Remember, it's the current that drives the motor. The purpose of doing SPWM is what? We want to get low harmonic, right? Now, our voltage is still like that. It's okay because the voltage provides the potential difference. It's the current that must be sine wave so that your motor will rotate very smooth. So, when we use SPWM, we can produce this beautiful sine wave as output, as you can see, which will have a THD of most probably less than 10 or 5, I'm not sure, I never measured. Because it is not connected to the grid, still okay. But this is one of the fundamental to get, okay, apply to a motor, because motor is what? It's induction. So it acts as a filter that will produce a sine wave. All right? And then like I said, it just like that is already good enough. Okay? Of course, variable speed drive depend on brand. The cheapest one, like I say, a few hundred ringgit. Expensive one, it depends on horsepower as well. It can go up to a few thousand, okay, to get one. Now you want to test, let's say, I want to increase the frequency to 60 hertz. Then, of course, you will see that the RPM will increase. Okay, you will see that the RPM slowly go up. $60 by 60, 3060, right? RPM. Yeah, 3060. So you will give roughly 3060, 50. The scope will show you how the motor will rotate from 0 RPM slowly to its nominal RPM. This is still a not control one. You can see we still have an inrush. You see, it still have an inrush. Why? Because the moment I start the motor, I want it to run at 50 hertz already. But just now you see the real one, it starts from 0, 1, 2, 3 slowly. So of course, in the real VFD drive, you need to write program to make it slowly so that you won't see this inrush. Because this inrush will trip your protection. Okay, but today what I want to show is that how SPWM will contribute to produce sine wave current and how this is used in the industrial variable speed drive. Now you can change, let's say you want to run it at slower speed, you can change it to 30 hertz. You run. So you virtually can change at any frequency you want. You know, like one of the application is the AHU, the air handling unit in many of the mega mall, our block A, you know, the fourth floor basketball court, they are using this. I mean, they are not using drive, they are using valve, mechanical valve. Okay, now you can see that the RPM has been reduced to 1,450. Okay, the nominal one is, you see, is 0.5, right? It start to oscillate. Okay, start to oscillate. Because I don't have any additional control, just merely simple frequency control. So again, no matter how the speed, now because the RPM is low, right? You can see there is no inrush. Okay, there is no inrush. But of course, the beauty is still there. You still be able to produce quite a decent sine wave output. Okay, by using the SPWM. Of course, you can play around, want to see what's the difference if I reduce this to 500 Hertz. Okay. Okay. Now you see the resolution of the sine wave is become lesser. You see more spike here, right? Because your switching frequency is only 500 Hertz. Just now I put 5,000 Hertz, is almost very smooth. Okay, so that is the difference. So when you design a variable speed drive, a grid converter, or off-grid converter, okay, the next class, I'm going to teach you how to design an off-grid converter with both voltage and current are in sine wave. For variable speed drive, the voltage is still the SPWM, but the current on this side, right? Okay, that's why this one you cannot use to power up your off-grid device. It only for motor, because it requires the motor inductor to produce a sine wave. So we will move one level up for off-grid application in the next class, and so forth. And please support a bit after lah. You know, I spend so much time doing this. Download the thing, test for yourself, and don't forget to like lah. Okay, you guys just download. No star. Wow, no more already, I tell you. Hey, give a bit lah. Okay lah, you don't want to get me 5 star. Give me 1 star lah. You see, I done this last night, you know. 0 star also tama bagi Alamak. Because I can see the download one. Only 7 download. Alamak, you guys Okay. So yeah, I think it's enough bullshit for today. Okay. Yes.
Regarding the design project, sir, for the presentation, do the other members have to attend during?
Not necessary if they are not free. Just the project manager for this week. But of course, if you are free, join lah. Support ma.
And one more thing, sir, for our team, for my team at Suntex, we have 2 hardware engineers.
Yeah.
So for us, we have to do individual presentation?
Individual. Yes,
So
individual.
I have to do my separate slide and my friend
Yes.
have to do separate, so I have to present separately.
Cannot be the same.
Can't be same.
You don't show the slide, you present the friend show the same slide. Tak boleh. Cannot lah.
Because we thought that we have to present together. So
No. It's individual. You have to tell me the assessor what you are doing and what the other so-called hardware or software are doing. Cannot be the same. Okay? Because if it's the same, your mark will divide by 2. Okay? Make sure I warn you already. You do.
thank you, sir.
Okay, you're welcome. Okay, any question in the online class?
Sir.
Still cannot get the answer.
No. So I want to ask, right? This one you are changing the speed of the incoming frequency, right? Instead of changing.
I changing what?
Because right now you are controlling the speed, right? By changing the incoming
frequency.
Frequency, yes.
Yes.
So in that the modular will actually change also the frequency of the.
Okay, you see there are 2 frequencies there for you to change, you know.
Yeah.
The one is the switching frequency. The other one is, you see there are 2 frequencies. Wait, I show the share screen again. Okay, still there. Okay, can you see my screen? Can, right?
Can, yeah.
Okay, now you see the modulator appear. This frequency is the switching frequency, 500. And this frequency is the frequency of, your sine wave, where you want to control the speed of your induction motor.
Oh, okay. Get it.
Get it?
Yeah, I get
So
it.
don't get this too wrong. You will damage the variable strip drive. So that's why just now I mentioned switching frequency, okay, and the frequency, okay, that you want to carry or modulate a different thing. All right?
Okay, sir.
Okay. You just try to download this and you play around. You should be able to see the difference. Okay, any more questions online? Okay, thank you. Okay, so if no question, then